In this lesson, we consider a most remarkable optical instrument, the human eye. We'll first describe the eye's anatomy and explain functions of the parts that are relevant to the formation of images. Then we'll discuss two most common vision disorders, the nearsightedness and the farsightedness. And we'll also see how to correct the disorders. In the figure, you can see the anatomy of the human eye. Incoming light passes through the opening in the iris. The iris adjusts the size of the pupil to compensate for changing light conditions. In brighter conditions, the iris passes less light by narrowing the opening. Light refracts in the cornea and lens, which together converge light to form a real image on the retina. Cornea refracts the light most, and the lens contributes only about 20 to 25% of the refraction. Retina has receptor cells called rods and cones that sense the image and send information to the brain through the optic nerve. For you to see a clear image, the eye has to focus light from whatever you direct onto the retina. The eye must adjust its focal length to compensate for viewing objects at various distances. This adjustment is called accommodation and is done by contracting and relaxing the ciliary muscles that surrounds the flexible lens. To view the distant objects, muscle is relaxed, making the lens relatively flat and its focal length relatively large. Viewing nearby objects requires a shorter focal length, so the ciliary muscle contracts to make the lens bulge. Okay, so that's the case when you are looking the nearby objects. Shorter focal lengths are no longer possible when people grow older. So the lens becomes less flexible, and the condition is known as presbyopia. The eye has far point, which is the largest distance for which clear images can form on the retina. In a healthy eye, the far point is essentially infinity. So our far point is infinity in normal condition. You can see distant buildings and mountains, even details on the moon. Your vision of distant object is limited only by their size. And for the near object, the near point is about 25 centimeters. So you can see any object that is placed at 25 centimeter very clear in your normal eye situation. If it is closer than that, you may have a little bit hard time to focus the object. So it will look a little bit blurry when you move it a little bit closer than 25 centimeters. Now, if the lens is too thin or too long, the image of distant objects fall in front of the retina instead of at the retina. In this case, the far object or the far point is no longer at infinity. So in normal situation, we have the far point at infinity, but now it's not at infinity anymore. It's somewhere here. Okay, that means you can see the objects clearly only up to that point. If you put an object here, you can see it clearly, but if it is away from that or farther from that, you will not see the image clearly. It would look blurry. So this is a common condition, which is called myopia or nearsightedness. So myopia can be corrected by glasses or contact lenses, as shown in the figure here. So in case of myopia, a diverging or concave lens is used to slightly diverge the light rays before entering the eyes. The net effect of this diverging or this concave lens is to diverge the lens so that the image is formed exactly at the retina. So basically the concave lens forms the virtual image of the distant object at the far point of the nearsighted eye. Okay, so here is the distant object, and this concave lens forms the image of this distant object at the near point here. And we know that you can see the object clearly up to that point. If you form the object at that point, then you can see the image clearly, which is what this diverging lens does. Nowadays, lasers are used to reshape the cornea to correct myopia. So the current technology used is called LASIK, which is laser assisted in situ keratomiliosis, in which the outer layer of the cornea is cut and flapped aside, and the laser then ablates and reshapes the underlying corneal tissue. The idea of LASIK is the same as corrective lenses, which is basically to increase the focal length and so that the images of distant objects fall on the retina. So the opposite of myopia is hyperopia or farsightedness. In this disorder, the eye is too short and images of nearby objects would focus behind the retina here. Okay, instead of on the retina, it's behind the image is formed behind the retina. So converging lenses in glasses or contacts correct this problem as shown in the figure here. The converging lens basically forms a virtual image of near objects at the near point of the far-sighted eye. So the actual near point is 25 centimeters, but because of the disorder, now the near point is far from the actual near point. So it's here. And this converging lens forms the image of this near object at this near point of the far-sighted eye, which allows the lens to converge the image at the retina. For hyperopia also, LASIK treatments are used, although with more difficulty because the outer edge of the cornea must be reduced in its thickness, which is really hard to achieve. So optometrists prescribe eyeglasses or contact lenses with specific focal lengths to correct a patient's degree of nearsightedness or farsightedness. Rather than specifying the actual focal length, they often use refractive power, which is defined as 1 over focal length in meters. Okay, so refractive power is measured in diopters, and to measure the refractive power in diopters, you need to use the focal length in meters. So for example, a lens with focal length of, let's say, 25 centimeters will have the refractive power of 1 over f, which is 1 over 25, and we need the focal length in meters, so that's times 10 to negative 2 meters. So that will give me minus 4 diopters. Okay, so a lens that has the focal length of 25 centimeters, negative 25 centimeters, would have the refractive power of negative 4 diopters. So let's look at a problem. An optometrist determines that a nearsighted patient's far point is only 44 centimeters from his eyes. Okay? So the patient's far point is 44 centimeter from his eyes. That means he can form the image. He can see the image clearly if the image is formed at 44 centimeters from his eyes. So find the refractive power of the eyeglass lenses needed to correct this problem, assuming that the glasses are 2 centimeters from the eyes. Okay, here is the picture. So you wear this corrective lens 2 centimeters from your eyes. Okay, and we know that to correct the nearsightedness, you need to wear this diverging lens or concave lens, because it converges, or it diverges the ray to help the lens to focus the image at the retina. Okay, so again, you need to form the image at the far point of the nearsighted eye. You need to form the image here. Only the image formed at that point could be seen clearly. If the image is far from that, or if the object is far from that, you won't be able to see it clearly. So that means you need to form the image here, and the image distance S prime would be the distance between the lens and the image, which is this distance. And we know that the distance between the far-sighted point and the eye is 44 centimeters. That's the far point. And the distance between the diverging lens and the eye is 2 centimeters. That means the distance between the image, where we need to form the image, and the lens, this external lens, would be 44 minus 2. So S prime is 42 centimeters. Okay, and this would be negative because from the sign convention, whenever there is virtual image, because this is the virtual image, and when the image is formed on the same side as the lens, we use negative sign. Now, object distance would be far away at infinity, and we need to find the focal length first to find the refractive power. So to find the focal length, we can use the thin lens equation. 1 over f is equal to 1 over s plus 1 over s prime. 1 over s is infinity, plus 1 over s prime is negative 42 centimeters. Okay, so 1 over infinity is 0. 1 over very large number is 0. And in order to get f, I need to flip on both sides. So I get 1 over f. I get f is equal to minus 42 centimeters. Okay. Now, in order to find the refractive power, I need to convert this to meters. So that would be minus 42 times 10 to negative 2 meters. So the refractive power is 1 over f. That is minus 1 over 42 times 10 to negative 2 meters. And that gives me, let's calculate that. So that gives me negative 2.5 diopters. Okay, that's the refractive power of the diverging lens needed to correct this nearsightedness.